my great pleasure today to be introducing Professor Andre Cire. Andre is an associate professor at the University of Toronto, an associate professor of operations management and analytics at the University of Toronto. His research revolves both around methodology and applications. On the methodological side, he works mostly on questions related to research problems in mathematical programming and dynamic programming. On the application side, his interests revolve around scheduling, healthcare, and inventory management. He received his PhD from Carnegie Mellon University in 2014. He's won a bunch of awards, notably a Research Excellence Award from the University of Toronto, and Inform's Computing Society, the Student Paper Prize, and the Best Dissertation Award from Carnegie Mellon University. What else can I tell you? He serves as associate editor for the Inform's Journal on Computing. So please join me in welcoming Andre.
All right, thank you so much. Everybody can hear me? Thanks so much, Phoebe, for the excellent introduction. I'm really happy to be here among friends, finally. And also, it's after lunch, so thank you so much for coming, even though it's after lunch. So today I'm going to talk, about decision diagrams for optimization. I'm going to focus on some applications in deterministic and stochastic optimization, right? So I cannot continue without acknowledging the great contributors and the great work team that we have here. For some reason, it's not updating. Oops. Let's go back a little bit. There is a delay, so don't worry, we'll adjust. So these amazing contributors that are always there, and they are really the ones leading, developing, as you saw with the great talk by John, and so on. And if I forgot to put your name here, let's let me know. I'll buy you a coffee, but I'm sure happy to see that this team is growing. Now, the work on decision diagrams, is an expanding area, just as you see the number of people that are involved there. There are a lot of works now that growing number of papers in different areas. There are a growing number of teams and theoretical computational advancement. Every year, every semester, there is a new work that is pushing the boundary. Now, all those papers usually they have some type of compilation techniques, how they construct a diagram that became an area by itself. Relaxations, how do you relax, how do you merge nodes? Also, we see talks about that today, how it's important to merge nodes appropriately and choose them carefully. Restrictions, how do you get feasible solutions from that? And today, we're not going to talk none of that, okay? Today, we're going to do something a little bit different. Today, what I want to talk about is modeling, okay? We're going to talk about models. So the question here is, why models? Why do I want to focus about models? So just to give you an intuition, right? We all know models, we all know and love them. A model shines light into properties, into methodologies, and into insights, both theoretical insights, new structural properties that you have about the problem, or new computational insights, better way to solve a problem, maybe a new type of branch and bound, and so on. Now, you have different types of models, each one, independent whether you're from machine learning, whether you're from more hardcore discrete optimization, you use different types of representation, right? Maybe you have a functional representation for a metric here. And here you're looking for functional structure, right? When you formulate your model as a type of a function, you're going to exploit convexity, maybe to solve the problem faster, so modularity to get some greedy approaches, and so on, right? Maybe you love to formulate your problems as I have to click it here close by. Maybe you like to formulate your problems as a mixed integer linear program, right? So what you're doing there is that you're exploiting and revealing polyhedral structure, more generally geometric structure. Then you start talking about facets, you start talking about modularity, decompositions, and so on. Make sense? And you can take the one favorite that you use. For example, if you have set, you're going to have specific structure from the sets. I just learned today about the PC, the propagated completeness, right? So each one of the problems, you have different structure. Now, what I'm advocating here is that why don't we exploit network structure even if we don't have it, right? I want to advocate for us to impose network structure even if we don't have it. In that particular case, then we're going to review different types of elements, different type of components that we're going to use for our methodologies. Maybe you're going to review some type of shortest paths. We're going to talk about nodes. We're going to talk about arcs. We're going to talk about node potentials. And that's going to reveal those different types of properties that we can exploit. All right, so we have to start somewhere. I'm happy that there were some more talks on decision diagrams this morning, so I don't need to go through very much, but just to make sure, a decision diagram is a layered acyclic network that encodes a set of solutions. Okay, and again, this definition is a little bit, I'm going to be a little bit loose. At some point, we're even going to lose the definition of the decision diagrams. I'm just going to talk about networks in general. All right. So, for example, you can have an optimization problem. You can pick your preferred optimization problem. It doesn't need to be linear. It can be nonlinear. It can have different weird structure. And then you can encode this as a graph, right? So the layers correspond to the variables of your problem. In this case, we have 3 variables, 3 layers. The arc, they correspond to variable value assignments, right? For example, you have a 0 arc here, a dash. It means that you're fixing x2 to 0 or x2 to 1. And then you have a one-to-one mapping between the arctic paths of this network and the feasible solutions of this problem, right? So every feasible solution has to have an associated path here. Every path has to have an associated solution. All right. And another important thing is that we can also associate arc lengths with the value of those solutions. In this particular case, we have a linear function. So linear function is easy, right? So if you pick a solid arc here, arc 1, if you fix the variable x1 to 1, you're going to have a contribution of 8. So you can just associate a weight of 8. If you have a nonlinear function, it's going to be a little bit more complicated, but you can do it. And in this particular case, the longest path is going to be associated with the optimal solution of your problem. Good. So this is the base that we're going to build on. All right, great. But what type of properties does this reveal, right? How can I exploit, how can I leverage this network to actually learn more about problems? And this is essentially what we're going to do today. This is going to be our journey, right? So we're going to take 3 problems and we're going to go dive deep. We're going to start easy. We're going to start with a walk in the park with a simple problem on rotation scheduling with one contributors at a diamond. And we're just going to lay out the key guidelines that we're going to use throughout the talk, okay? Then we're going to move to something a little bit harder, second gear, where we're going to talk about competitive project choice. Okay, we're going to talk about Bilevel optimization, robust optimization, and I'm going to introduce something a little bit weird, which is going to be parametric networks, but they're going to be amazing. Amazing. Finally, we're going to lose our minds. Okay, lose it. We're going to talk about learning with decision diagrams, but in a particular setting, we're going to solve approximate Markov decision process using these networks that we're going to be in a learning process. We're going to prove new properties of multi-arm bandits, of classical multi-arm bandits, by just getting these network properties that we have here. Okay, so it's going to increase in intensity, but we can do it. Ready? Are you ready to? Perfect. Okay, so let's start. Okay, first, easy, a walk in the park. Okay? So let's talk about rotation scheduling. One day, I got a call. Okay, so this call was a medical school that actually they want to help with their clinical rotations of students. Okay, so it's the last year of medical training. It's a really, really difficult process that they go through. This is actually real what happens. It's a very tough year. So basically, they rotate across different specialties. They go to surgery, family, medicine, in multiple hospitals. This is what they go through. And I was surprised when I saw the numbers. It's a multi-million-dollar process. The hospitals, they spend so much money in allocating capacity to different places, in sending students, in paying travel for students to go to these rotations in different countries. So it's a complicated process, okay? The problem, it doesn't look so hard, right? Essentially, what you have here is you have to sequence and schedule the rotations for each one of the students. So how does the rotation look like? You're going to have a student here. Then the student is going to do, let's say, the first rotation surgery on January 22. You have to specify the dates as well. Then the student is going to do an emergency rotation in February. Then the student will finish off doing family medicine on January 23rd. So you just need to define those sequences, schedule them through time, and do this for all the students. What is the challenge here is that you have complex capacity and quality of service constraints. Not surprising, right? You saw the students dying over there. You want to make sure that they are at least happy a little bit. So type of constraints, you don't have excessive idle time. So for instance, maybe this rotation is not so good because you have more or less a year of difference. The hospitals are going to have capacities, right? Not all hospitals, you have a number of surgery slots that you have a particular periods, but this is more or less flexible. So the medical school can give donations to the hospitals that it can increase capacity. It's a real thing. And you have large scales, you have around 300 to 350 students, right? And I can see through your eyes. The first thing that you're thinking about is mid per CP, right? I can already see the ILO intervals in your minds, or the SAT solvers over there. You can see the clicks here of the type of models in general. Yes, but should we? Should we? So one of the contributors of the work, it was one of the best models that I see. This is how the MIP looks like, right? And I'm sure that you can do better, okay? I know that you can take your set solver and you definitely can do better than what we did here. But the question is, should we? These models end up being so complex and there are a lot of idiosyncratic constraints for you to put all of them at once, right? So we tried different models. None of them, they scaled appropriately. You can do other alternatives. Sure, you can do abundance decomposition, column generation, where you generate the columns, and you can do all of that. Sure. But what about networks? What if we model these problems as networks? Okay, so what can we do here is we can maybe encode the set of feasible rotations for each individual student as a type of network, right? So what would this network look like is something more or less like this. Each path represents the story of a student, right? I like to say, oh, this is our storytelling decision diagrams when I'm studying them, right? So they tell the story of a student throughout the term. So essentially, you're going to have an arcs that are more or less a tuple, and each arc represents a hospital or rotation in a month. So it's a little bit different than what we do usually in sequencing multi-value decision diagrams, where I'm also incorporating the time into the arcs, right? And there will be some advantages there. So if you look at the path from root to the terminal, essentially what you're going to have, after you spend some more with it, you're going to have the journey of a student. Each path corresponds to the journey of one student. Good? All right, that's it. That's the representation. And I already know the question, okay? This network's going to be too large. And then I only have one answer for you here. True. They're going to be exponentially large. They're going to grow immensely. But maybe we can be a little bit smart about it. And we actually can prove that when you select constraints carefully, when in particular you throw away some knapsack inequalities, then the upper bound of the number of nodes and arcs that you're going to have is this complexity here. You're going to only have one exponential term in this k elements. What is this k elements? Is the number of rotations that a student do. And the number of rotations that a student do is 6. They are super small. If you ever work with multi-value decision diagrams and you have the set constraints and the set states, they grow up on the set states. And the only different constraint here is that the student cannot do the same rotation in a time or cannot do the 2 rotations during their journey. So these networks are small, as long as you throw away some of the constraints, right? But then you're going to have an issue that, well, I need to have put these constraints back somehow, right? So how do I actually construct the full model now? How can I design the full model? Because I only have a few of the constraints, I only have some of the difficult points. So the way how we can do this is that, think, if each one of the paths corresponds to a student story in the system, then essentially scheduling m students is equivalent to send m units of flow from the root to the terminal, right? Each one associated with student. The flow has to be integral, of course, but it's sending m units of flow. So in this case, we're going to have a polyhedral description of the set of feasible solutions through here. And now what we can do is that we can simply construct a model where I can create a MIP, where all the knapsack constraints for MIP is excellent at, I put here in the MIP, and the flow inequality is describing how the rotations of the student work, how the story of the students are encoded in the network. So I have a network flow problem here with additional constraints. And that's it. And that's it. Okay, so it works great. It works great. So our best MIP model, our best CP model, couldn't even get close to all the solutions that we could solve at a particular time, and I can give you all the details. And they also loved it in practice because I know some people think, oh, this is knowledge compilation, exactly, and they could go there and they were happy to adjust the network. They understood what the network was, and they actually removed some paths. Oh, I don't like this rotation, so they just adapt the network a little bit the way that they want it, without having to add all the descriptive constraints. And that's it. Yes?
Sorry, I think I missed it. How did you solve the problem on this page?
It's a MIP. We just threw it into a MIP solver. We just threw this into a MIP solver. We construct the network and just threw this into a MIP.
How do you represent this flow y and flow bi?
Right. This flow I is this inequality here. If you have the flow balance constraint and the input flow is m. Got it?
Yes.
Great. Good. Right. Simple, but effective. Okay. And you can do better models that solve this with decomposition and so on. But this was effective. And what I want to highlight in this example is, first, we can use network models to capture difficult structure of the problem. In this case, we use use the network to capture those sequencing constraints. Because if you put in a MIP, you're going to have a lot of big M's. If you put it in a CP, you're going to have to assign and sequence, and that's complicated in CP, right? So also, we would leverage the network to capture some structure. In this case, the network was compact if you threw away some constraints. So this is a property of the network that we could exploit, okay? Especially we also use reduction, we also use other structures. And finally, we exploited this network flow perspective to actually link different models, to put the models together. Good? So these are the guidelines. Now I'm going to apply this guideline through the rest of the talk. Make sense? Yeah.
That's another question.
Absolutely.
So the network is not unique, right? Or is it unique?
It's going to be unique.
So
yes.
So is there one path for every feasible rotation?
Yes.
But not one arc, one path.
One path.
But the
one
arcs
path.
can
yes.
be around. Okay.
Yes, and it reduced order net decision diagrams. They're going to be unique. There are properties there. Yes.
It's unique with respect to the order.
With respect to the ordering, right? Yeah, but this ordering is natural, right? I'm going to do my first rotation, second rotation. You can switch the order, but I don't. And then is the state. I don't know how the state's going to look like. Okay, good. All right. Can we push second gear? All right. Our next problem. I actually got another call. Okay, I got another call. And this was an organization facing a challenge. It was a very interesting problem. It was a known problem. Okay, this is how it works. They need to choose marketing actions. You can think about they need to choose YouTube and Instagram to sell, to maximize impressions. Okay, so essentially they have some influencers that they wanted to pick to talk about some events and activities they were doing at the time. And what they had to do is that they had to select some YouTubers to try to sell that particular product. Hey, there is this event, come here. Okay. Now, they could not select all of them. Maybe they just selected 3 here because they had budget constraints and some other combinatorial type of constraints that exist there. Okay. The thing here is that there was also another organization that was competing with them. And actions or the marketing assets that they wouldn't pick would be selected by an adversary, right? The leftover influencers here, the adversary could pick them up and then they could try to advertise their own product that was competing at the time. Make sense? Okay, so how do we formulate this problem? Well, we first gonna have this assumption, maybe not true in practice, that the follower that we call the second one is gonna act rationally, right? They're gonna do the best that they can. So we are assuming that they're gonna solve their own optimization problem with the remaining influencers that they can use. So they're going to solve, let's say, a simple budget constraints, a single inequality here, single math programming problem. Okay. Now, the real problem that we want to solve is we want to maximize the reward minus this opportunity cost based on what the adversary did. So this is how the problem looks like. Okay. If we're going to have a linear object function, just to simplify, you don't have to. We're going to have a single linear object function. We're going to the main problem is going to have also their own constraints, their budget constraints. And then you're going to have that the follower variables, the series of the variables are optimal. They have the argmax. We saw this in machine learning yesterday, right? The argmax elements, where they're going to solve their problem, but now you're going to have this class of constraints here. That if the leader pick one of the variables, the follower cannot pick that variable again, right? So these are known as interdiction constraints. Make sense? Great. So this is a large class of combinatorial bilevel problems, right? Because the value of the variable has to be the set of optimal solutions of the follower problem. Good? All right. So it is this simple interdiction constraint sounds simple, but actually it models a number of problems. I was surprised. Network interdiction problems, vertex edge blocking, and many, many others are in this class of problems. Okay? They have different constraints, but the basic interdiction constraints are going to be there. The challenge is essentially this constraint here, right? How we represent this constraint, because how do we represent the set of optimal solutions of a problem? And there are a number of techniques. For example, if this problem were a linear program, we could use a strong duality, right? The prime and the dual are the same, so that we would have a description, a feasibility description of a set of optimal solutions, but it's still not easy. It's still going to have a non-linear problem still not easy, okay? Still not easy, but you can do it. At least you're going to have a single level non-linear problem. The state-of-the-art methods, if you pick them up, there are a lot of people that work on this, Matteo Fischetti, Ted Rolfs, they relies on type of a branch and cut methods. Okay, they generate cuts based on this subproblem, right? I can send you the references, a lot of nice things there. All right, What about if we represent that constraint as a network? Okay, we are going to push a little bit, but we're going to make it, okay? So suppose we're going to represent the following constraints as this network-based formulations. This is the constraint that I want to represent. I want a network where, somehow the solutions are satisfied this constraint. Well, I don't know how to do it, but let's suppose that we're going to ignore the interdiction constraints for a little bit, okay? So I'm just going to throw these interdiction constraints away. Oh, but now this, I know how to do it, right? I can formulate as a network problem, and then the solutions of the system are going to be the longest path of this network, correct? So here I have my beautiful network. Now, what happens? What happens is that, what is the leader problem doing? The leader problem is trying to prevent the longest paths from occurring, right? So that it could maximize its own cost. So let's say the follower comes, oh, I'm going to give you this solution here. The leader can come and say, no, you won't have that. I'm going to pose a constraint that is going to block this arc. So then it has to choose another longest path. And this is the game that the leader and the follower are playing. Make sense? Okay, great. So what type of problem is this? So what I'm going to do is going to write, it's a little bit more general, right? I'm going to write as this, as a minimization, right? So we're going to have the problem where y is a path in the network, okay? So I just wrote it differently. This is a type of model that I have, and I'm going to represent those constraints. When I look at those constraints, this is how this constraint is going to look like, right? I'm going to have this G, this coefficient matrix based on the XL, parameterized by this XL, and the right-hand side. What type of problem is this if XL is fixed? Do you know? This is the famous constraint shortest path problem. If you've never seen it before, it's everywhere. There's a paper every 10 seconds about that. Even in OR 2 months ago, there was a paper about that. Because it's such a pervasive problem, right? You have to find a shortest path satisfying some type of constraints, right? They're using multi-objective optimization. They're using a number of different problems. And actually, even the paper, by the way, all the papers are open. If you want, I can send you. The paper, if you can, actually, we can solve this problem using dynamic programming. It's super fast. If XL is fixed, we show that it's better than use bit, blah, blah, blah. But the problem here is that we have this parameter XL, correct? Now, how are we going to handle this XL here? We have to use the right model. So let's change the model here. Let's formulate this using a type of a network flow model. Here. What type of property do we want to have in this type of matrices so that we can, for example, preserve the longest path, shortest path structure? What type of property we love about linear programming? Then we see the matrices. Total unimodularity. So if I use that, if this matrix is totally unimodular for all types of XL, I know that the solution is going to be a shortest path, right? And then there exists a compact polytope when I mix the primal and the dual, that when I mix them together, I'm going to have a description of the longest paths or the shortest paths, whatever do I want. So guess what? These single constraints that is everywhere satisfy these properties because they are just domain constraints. It's just limiting the domains of the arcs. So they're going to be totally unimodular, right? So we can rewrite this constraint here as a particular feasibility system. This is going to be equivalent to, I'm going to have my primal feasibility constraints that I have to have a flow. I'm going to have my dual feasibility constraints. But notice that I have this delta here. So remember when you have the node potentials in shortest path, when you take the dual of a shortest path, you're going to have the pi I minus pi j greater than equal to Cij. Here you're going to have the same thing, but you're going to have a corrector factor because of the duals of this additional constraints, and you put in delta ij is a correction factor. And then you can put a strong duality here saying that the primal solution has to be equal to the dual solution plus some correction factor again because of the dual variables. Make sense? And you have to put, this binary variables here. Again, you have to put the binary constraints because of the degeneracy, right? To make sure that you're not ending in, if you have multiple optimal solutions, you want to be in an extreme point. Good? Great. So we have a feasibility system, but we can do more. We can now leverage the network structure to learn more about this. All right, so how do we do it? So I'm going to show the intuition. All right. What is this problem? When you think of how this problem works, these parameterized networks, every XL is going to define me a particular network. So the set of solutions is actually a collection, a family of networks. So for example, if I fix XL to a particular value, to a particular binary value, I'm going to have some network where some arcs are blocked. And for all of them, I'm going to have a different family of networks. So if you put all of them together, you're going to have this big, happy family of networks that you want to solve. All right. Now, this means for any fixed XL, the optimal basic solutions, they're also going to be a longest path or shortest path. Make sense? Because when XL is fixed, then you maximize, it's going to be a longest path, right? The optimal basic solution when you're in an extreme point of the underlying polyhedral. So in some cases, you can actually prove that arcs that are blocked, okay, arcs that are blocked, they're going to be always at their bounds in some situations. That's, you have a constraint that y less equal to 0, y equals to 0, so it has to be 0, the particular flow variables. So there are some technicalities, but the main thing that we get from here, from this observation, is that one of the main things, if the Fowler coefficient matrix is non-negative, then I know the value of those corrections. It's going to be essentially the value of the arc, because this is essentially how much I'm losing for blocking that arc. This is what this delta they mean. Okay, and there's an asterisk here because if it is not a star here, because if it is not non-negative, you can still get an expression, but it's ugly, and I want to make it look nice here. All right, why does that matter, right? Let's think about that inequality that we have here. We can take these delta ij's and we can replace it by the blocked arcs, actually. So if you select these arcs carefully, you can rewrite this inequality as this one, where this A prime here are the blocked arcs, but this is what you get. Now, what is nice about this that you don't have here? What is great thing about here that here it makes us very sad? Exactly. No multiplication between the dual and the leader's problems variable. Here we have a system that is totally linear. This means that we can simply put the system all together to get a new type of network-based extended formulation that I have not seen before, but this is how the formulation looks like. It's a completely extended formulation of this system, where we're going to have the linear variables, the network flow balance constraints, dual constraints, and that's nice dual inequality, strong duality inequality. It's a single level mixed integer linear programming formulation for all the classes of bilevel problems. And yes, I understand that the network may be large. But if we take the classical benchmarks of these particular problems, oops, did I miss it? I missed it, sorry. Let's go back. There is a small delay, we'll make it. If we take the classical benchmarks, just by using these networks, because these bilevel problems are so difficult, that the networks were actually not that large for this class of problems. So comparing to the time between the branch and cut, the Fiscari one, and the DDR, this information that we have, in many cases, we were getting orders of magnitude improvement. Not always, sometimes it was worse because of some properties that the branch and cut could exploit more. And the cases where the networks, they were too large, were also the cases where the current methods, they could not solve yet. And again, this is just the model. I just model there and just put it there. Imagine if you investigate relaxations, if you investigate other better ways of constructing these networks, better models. So there is a whole new thing that we can go from there. Make sense? All right. So just because we use the right model. All right. That's it. So let's recall the guidelines. Okay. So we're going to use the network to capture these different constraints. We use the argmax in this case. Sometimes non-trivial inequalities or non-trivial constraint systems you can represent better as a network. Then we leverage network structure in a little bit deeper way now to get better insights or some theoretical structure that we could use. For example, use the total linear modularity of that system, and we linearize via some properties of the dual. And finally, we use the network flow model in this case to construct the whole model that we needed. Make sense? All right. Okay, let's go to the next problem then. Last problem. Deep breath. Okay. Ready? Ready? Okay. All right. I didn't get a call this time. It was an email. Okay. Yeah. Okay, so we're gonna go. Some people are gonna see this problem right away, but let's go one step at a time. Okay. So a retailer wishes to run a seasonal sale for T periods. Okay, think that it's some sort of a limited time promotion or summer winter sale. All right. So the problem is that during the sales, the retailer needs to choose which assortments they're going to put in their website or that they're going to try to sell, right? So, for example, it was late at night. I was thinking about mattresses for some reason. So I just searched for mattresses. And if you go to a seasonal sale of mattresses, then you're going to see that not all possible mattresses are going to be part of the sale, right? So you're just going to see online a few of them. That's exactly the problem that they want to show is what is the assortment that I'm going to show in this web page or during the seasonal sale for the weekend or for the summer. Okay? Right. So there are a number of challenges in this particular setting. So the first challenge is that the demand is unknown, right? That's where we're going to get into uncertainty here. Demand is not known. Okay. So there are different ways for you to address this. You can get the distribution from previous years, but now I'm thinking about a sequential process here. So the retailer is going to start with a prior belief of what the demand distribution looks like. So the retailer doesn't know the demand distribution, but it assumes that there is a class of the demand distributions that they are working on, okay? And then at every period is updating them periodically. At every stage, it observes the demand, what happened, and it's going to update it, okay? So the classical model for this is, for example, the Gamma-Poisson Bayesian learning, right? That I'm sure the machine learning here is learned the first day that they were born. Oh, Bayes. So, for example, what is this? It assumes that the demand is a Poisson, but we don't know the rate, we don't know the lambda. So we're going to use a prior belief of the distribution of those lambdas. In this case, we're typically going to use some type of gamma. So let's say that I have two periods, okay? So let's say that I'm trying to sell now laptops. So if I'm at the money Poisson, my prior belief is usually going to be represented by this gamma with these two parameters, m and alpha, right? And then, if you saw that, what is the probability of observing a demand here? It's going to be a negative binomial. But essentially, at the end of the day, I have this prior belief. And at the end of the day, I'm going to observe the demand. Let's say 10 people bought my laptop. So then with this information, maybe it has a very low probability of having 10 based on my prior belief. So then what I can do is that I can update my distribution here to represent that more accurately, right? So in the second stage, I'm going to update. I'm going to have an m prime, alpha prime. It's a simple update when you see just a summation. But I'm going to update my prior belief, my distribution of the possible demands. Then I'm going to observe this again, and I'm going to continue the system forward. So then at every period, I'm learning more and more about my demands. Good? Make sense? Yes?
The assumption the products don't interact?
Yeah, I'm assuming they're completely independent. Yes, I'm assuming a lot of things, okay? I'm assuming a lot of things. For now, okay? Thank you. Great. The issue here is that you cannot offer all products at every period. Like there are 50,000 SKUs and it's wild. So they cannot offer all products at a particular period, right? So then what happens is that the assortment choices are often combinatorial in nature. So let's say they have a selection of products here and they have to pick the products to sell or to choose at every period. So for example, maybe you're going to have budget constraints. You cannot pick all the products. Imagine someone getting to a website and seeing 50,000 products in the website. Nobody's going to buy anything, right? So we have a budget constraint there or the capacity of shelves even, right? The volume and the capacity of shelves. And you may also have compatibility constraints. Maybe you don't want to show two products at a time because they may have some sort of, they have some cannibalization, right? There are two laptops that are competing brands. If a person buys one laptop, doesn't buy the other one, things like this. Okay, so and this can be very combinatorial, can be independent set constraints, can be knapsacks, and so on. Good. All right. So this is essentially what John was saying here, right? It's a classical example of the trade-off between exploration and exploitation. So essentially, what should we do to maximize expected rewards? Should we offer our products more during more periods, right? To learn more about the products and with the hope that the demand is much higher than what we expect? Or should I just take the whatever knowledge that I have and then sell the products that I with the demand information that I have at the time, right? What should I do? How should I balance this exploration and exploitation? Make sense? Right. So essentially at every period, you're solving a different type of you're solving a different combinatorial problem, right? To select the products based on the updated information that you have at every stage, and you want to make a decision at every one of the stages. So this is a dynamic system. What is the most classical problem that this represents? Who knows what kind of problem this is, for instance? Does anybody know? No? Okay, this is the multi-arm-Bennett, exactly. This is the classical multi-arm-Bennett, right? Though the multi-arm-Bennett problem is usually they just have one single knapsack inequality, right? That you choose, you have a cardinality, it's called also dynamic selection problems. You choose, 5 out of 10 products, right? So you can have more complex ones here. And here I'm just considering a very classical version of the multi-arm-Bennett, okay? In this case, I'm maximizing rewards. I don't think about regrets and so on, okay? All right. So how to solve this? Well, this is a class of problems known as weakly coupled dynamic programs or weakly coupled Markov decision process. Because you can think of each individual product as an MDP by itself. It's running, you're learning separately, but then they have a linking constraints represented by the combinatorial ones. You cannot show all the products, so they are linked at every one of the stages. Make sense? All right. Can we solve it exactly? Not even think about it. It's super, I cannot even express how hard those problems are, okay? So a majority of the work here is in the seminal area actually is in approximations for Markov decision process, specifically for these weakly coupled dynamic programs, okay? So look at the people working. You have Dan Elderman, you have Bert Siemens, you have Dave Brown, you have Philippe Caro, you have Gallian. So big names here that such an important problem that work on here. And then you have different types of relaxations. And there are a lot of applications here, as you know, optimization and machine learning. So I'm going to give you a key summary of the main approximation that they have in this area. Okay? The key approximation that they use, because we cannot solve them exactly, is essentially a type of a Lagrangian relaxation that is going to decompose the Markov decision process per product. So for example, let's say that in each one of the periods, the constraint that links them is a single knapsack. It's just this one here. So more generally, we can write as this one. You have ATX less than equal to B. And then if you, I'm going to take these constraints, I'm going to associate a penalty with them. Okay, the penalty of violating those constraints. And you can think exactly on Lagrangian 101 that you learned in the first MIP class that you had, right? You're going to dualize these constraints. You're going to put them into the objective function. Okay, so when you put in the objective function, then you're going to solve each product individually using dynamic programming. All right. Again, it's a Markov decision process, but it's individual per product. So essentially, this is how the problem looks for an individual product. You're going to have here, you're maximizing, right? You're going to decide whether you're picking the product or not. Okay. So then you're going to have the expected reward minus the penalty of picking that product. Just like if you were dualizing a linear inequality, okay, the lambda times the coefficient of that constraint. And then you're going to have another part here, which is the future expected cost based on the updates that you can have. So if you observe them, you list all the possible observations that you can have. The state here is essentially your knowledge of the products, those M and alphas. This is your state here. And this is solvable. The state space for each individual product is not that large. It means that during the sale periods, let's say it doesn't grow too crazily. Still, it's manageable. You can solve this kind of fast actually. All right. So the Lagrangian problem essentially is solving this Lagrangian dual bound. So we're going to maximize the multipliers, lambdas, subject to the sum of each one of the products individually. So you separate the products, right? Plus the Lagrangian penalty. You're finding those lambdas. Good? Makes sense? This is actually a bound. This is going to give you an upper bound on the maximum reward that you have because of the properties of these problems, so you can prove this. And essentially, the approximations, now, how do you get a policy now? How do you get a final solution? Once you have the lambdas fixed, once you figure out these lambdas that you can use different methods, even subgradient and everything. Once you figure out these lambdas, then you can calculate these functions V's, and essentially I pick the products that maximizes those V's. That's how I extract a policy from this. So this is called greedy optimization in the dynamic programming community, the MDP community, right? Because this is going to give you a value for approximation. It's going to approximate the continuation costs, the future continuation costs. Good? Right. Now, a number of works based on these principles. There's even an OR paper, I think, Learning to Rank, that says a multiplier. It uses the same idea. I think it was yesterday. So you have a number of techniques based on this. You have indexing policies. For example, you can show that solving these optimization problems, you can rank the products by the maximum lambdas. You can prove properties on how bad your relaxation is, that they also extend to the deterministic case. So how bad is a Lagrangian depends on the number of constraints that you have. So lots of interesting results that they have there. We're going to do something different. Okay, we're going to do something different here. We're going to go a little bit wild. We're going to change this approximation based on this idea of networks, and we're going to see what happens. Okay, so what are we going to do? So there are several ways to perceive what we're going to do next, but first, it is well known that the Lagrangian problem, the Lagrangian dual problem, you can solve as a linear program. So this is how the linear program looks like. You have that dual problem object function, right? The dual problem object function, and then you change the max for these inequalities here, right? So the variables are going to be both the v's and the lambdas, and you're going to replace the max by all these inequalities. And some may say, hey, this is non-linear, you cannot have this. But look, we are enumerating all the xi. So we're going to construct, because x is discrete, we're going to list all the possible values, and this is how we replace the max. Good? And I know some people are going crazy. No, but the 8, no, radical acceptance. Okay, let's accept it now. Okay. What do we do when you have a linear programming model? We take its dual, right? So how does the dual look like? So, omitting some notation, if you are aware, if you are familiar with MDPs, when you get the dual variables, they represent frequencies, right? So essentially, these pi's are the frequencies that at stage t, you are at state s, that is, you learn something at this state, and you apply the action xi. So essentially, was what John was saying when he talks, right? You get these pi's here. So it's the probability of offering the ith product at that particular state when you learn some products here. And this is an expectation, right? The expected reward. And here, this is our flow, transitional flow probability. So essentially, if you never offer a product, you're never going to learn anything. So this is what is represented, that at every stage, depending on your actions, you're going to have different probabilities depending where you are. Okay? But remember, we have that particular lambda as variables in the LP prime. What happens? What's the constraint that is representing the dual? And this is key for insight. Okay, again, we're thinking about models, what they reveal. This is what this constraint looks like. We're going to have the coefficients times pi less than or equal to b, the right-hand side of the constraints. What does this represent? What does this look like when you look at the dual? Do you know? Does anybody know? What? Sorry, it's an inequality, but these are probabilities. When you sum them over all the possible cases with a's, what does this give you? Sorry? Well, this is an expectation. This is an expectation equality. So this means that the constraints are being satisfied on expectation, the linking constraints. In other words, what is the Lagrangian doing? The Lagrangian is creating a policy that is something like this. I'm going to look at a state, and if at the state that I am at the moment, that I transition at the moment, I apply an action based on those probabilities, I randomly pick a policy based on those probabilities, and I keep doing this, in the long run of the system, if I keep repeating the system, then I'm going to satisfy the inequalities on expectation. It's a random, it's a probabilistic policy that if I randomly pick these probabilities, then I'm going to satisfy the inequalities on expectation. They're not feasible, but on expectation, they are feasible. This is the basis, for example, of a number of fluid models in optimization. Okay, we're going to change this. Okay, we're going to change this. The idea is that why don't we satisfy these constraints with probability 1 and not only on expectation? And not only on expectation. So essentially, what I want to do is that I want to remove this constraint here, and then I want to create a probabilistic policy that at every period, I'm going to randomly pick a solution, and I want to make sure the solution is feasible. Okay, sounds good, but how are you supposed to do that, right? What about we use networks? How are we going to do this? Well, The idea is that I'm going to use the networks to represent a flow of probability or frequency at which we visit the path. So essentially, at every period, instead of taking these probabilities from the Lagrangian, I'm going to take these probabilities from a network. I'm going to randomly take the flow of a network, I'm going to look at the probabilities of the network, and I'm going to randomly pick them. And that's going to be a feasible policy for my system. So, in other words, at every period, I'm going to have a network, all right? What are the arcs of the network? It's a little bit larger network for sure. What are the arcs of the networks? They're going to be a state-action pairs, as opposed to being just actions, just as xi. What is the state here? The state is the knowledge that I have accumulated so far. So I'm going to have one arc for all the possible states. Remember, they are not that large. And the states here represent, for example, those parameters m's and alphas. So I'm going to have a state, and I'm going to have the action that I'm applying. And through this action, I can make sure that all the paths here are feasible, for example. All the paths are feasible. So a flow from R to T in this network is going to represent an assortment given that I'm a particular state. So let's see an example. This is how, in our case, that this path looks like. I'm going to have the state that I have, the action, the state that I have the action, and the state that I have an action. Okay? I can construct this network to make sure that this assortment here is feasible to that particular state. And I'm going to make sure that I have an arc for all the possible states that I can be at. This means that if I have a flow in this network from R to T, or if I have a number of flow, I can always decompose into paths where the paths correspond to feasible actions, and they list all the possible states that I can be at. Okay? You look at me like, oh, good. All right, more or less. Any questions?
So how did you go from that path to the assortment?
Now we're going to compute a bound based on this. Okay? So then I can tell you how we're going to extract. So every solution here is going to be a feasible assortment. So we don't need to do grid optimization anymore. We get a value function approximation, but we don't need to do it anymore. So what is the final formulation? Essentially, for every period, I'm going to construct these networks. If I have an infinite horizon problem, I just need one of them. But if I have a finite, I have to create one network for every period. Sometimes they're the same. And essentially, what I'm going to do is that I'm going to ensure that I have flow constraints for each one of them. And I'm going to have arcs linking these different networks. So this means that if I apply an action here at a particular state, I have a probability of transitioning to another state that I want to link to another arc in this other network. And I have a flow of one entering this network. So I'm going to have two flow of balance constraints. Flow of balance for each one of them. And I'm going to have the flow from one stage to the other, representing how the probabilities they transition. So if I apply a particular action at a state, I have a higher probability of going to a particular state. If I offer the product, I have a probability of learning something about that product. Make sense intuitively? And this is the model. This is the model that we have. So essentially, if you think how the model changes, is that I'm going to have an extra index U of those probability variables. So it's the probability of that particular flow crossing the node U. Instead of having only the state and action, I'm also going to have a node here associated with my stochastic network. Okay. Right? It's nice that it's complementary to work by John. I think there are different ways of representing this system. And now also going to have conservation of flow and other auxiliary constraints. Okay, so far? All right. And again, I can give you all the papers and so on. But for the sake of time, let's just talk about some quality. Okay, what is the quality of this bound? So here's the thing, which is nice. Okay. First, this bound is going to be better than Lagrangian. Right? It's going to be better than Lagrangian because we are satisfying the probability, the constraints at every stage. It's not going to be exact because there's another relaxation that we have to do there. But this bound is going to be the same as the approximate linear programming bound. This is what's great about it. So what is the approximate linear programming bound? This is one of the most important bounds that exists, but nobody can get it, right? So what is this bound? It's from this classical work, the linear programming approach to dynamic programming. And essentially, you're doing a regression with your value function. So you have your original value function of your DP. You're approximating as the sum of different base functions that we have here, each one for each one of the products. Some people, when they're doing AGP or they're doing approximate dynamic programming, they use linear basis functions and so on. This bound is the best bound that you can get with all the possible set of value functions that exist in the universe. Okay, what is the best bound that you can get when you do this linear regression on the value function? And it's too complicated to calculate. But if you do this network approximation, we actually recover this bound. It represents a linear regression over all the possible basis functions that you can do. And it makes sense because the network is additive, right? You're adding the values as you go through the path. So they can also be large, that is true, absolutely true, but is it, right? So they're often much smaller than ALP, much smaller. And something people they were only able to solve small problems with ALP as this bound, but they are better than that. And the thing is that we learned is that we have been greatly exaggerating the difficulty in calculating these approximate linear programming bounds. If you're familiar one, every paper that you read, they say, oh, we cannot do it. So actually, there are lots of problems that we can do it. In particular, it is polynomial for a number of problems that people have solved. One of those problems is the multi-arm band problem. Here, the network is going to be polynomial sized for so you can get the ALP polynomial time in the input of the problem for multi-arm bands. Okay, so there's some numerical analysis that we show that the first time that we can run knapsacks and we can show that it's better than the Lagrangian, and we can have a better idea when it's better than the Lagrangian. There are papers about this, and the first time that we can actually do computational results computing the bounds. But I know I'm out of time, so I just want to conclude, okay? We didn't leverage network structure or other things yet. So let's do it now, okay? Let's do it now. So there are surprising structural insights that you can learn from this, okay? For example, I told you about that difficult bound, the ALP bound, right? That people cannot compute it. It's classical in dynamic programming. And one of the open questions that people have is, when does the ALP bound match the Lagrangian bound? That's one of the open questions. And if you look at the literature, everybody tries to get it, right? Everybody tries to approximate. Alderman, he gives an example for the right-hand side of 1. Bert Siemens also showed for a knapsack inequality, the knapsack cardinality, a special case with larger. More recent, a paper that was 2 weeks ago, David Brown, we were in talks to them. They also proved some properties there. We're going to do it together, okay? And look, these people are good, but it's just that now we have a model, and the model shines lights into different properties, different things we can do. The model that we have, and again, it's something that people always work on the value functions. Here we're working on the networks, on the flow model. And I have a question for you, okay? So we have our network reformulation, right? We have our network reformulation, and we're thinking about these extreme points and so on. If you have an IP, you have a model with an IP, you have the linear programming relaxation of your IP. Good, everybody saw that once in your life. When does the linear programming relaxation of an IP matches the bound that you get when you dualize a constraint? When does that happen? What is the property that you need to have that when you dualize a constraint, your Lagrangian bound is the same as a linear programming relaxation? Do you remember? I see. Do you know? No? You learned that in Lagrangian MIP 101. When you relax a constraint, and your Lagrangian bound remains the same.
You need the remaining LP to be the convex hull.
When is the convex hull?
The thing that stays if you don't relax.
Right.
The convex hull of that has to be the same.
So what is the property of the linear inequalities when the convex hull matches?
I guess they're ideal.
They're ideal, which means that they are.
They're integral.
Sure, I'm going to get from him.
Where is my doctoral student?
So what is the property of the coefficients of that matrix?
You have 5 minutes, so I hope he's quick.
He's quick. It's going to be quick. Do it, man. What's the property of the matrix, the coefficient matrix?
Oh, it should be totally uniform.
Totally uniform. That's it. So closed. Sorry. The ALP equals the Lagrangian, where the Lagrangian matrix, the resulting matrix here, is totally modular. That's it. And it's a question that was open because we just had a different perspective. Not that it was difficult, it's just that we had the right model. And that's the goal, is showing that we need to have the right model. Okay. All right. Now I'm the right one. Thank you.
We have time for questions.
Okay. Yeah.
The first project that you presented,
Mhm.
you have your kind of nominal model,
Right.
and then you have your bit with the network flow.
Yeah.
Do you have a sense of like what's the intuition for why the second model is easier to solve as an solver? Is it because it has more continuous variables and stronger relaxation?
It's a stronger relaxation, and it has less variables. It has less variables. Yeah, because you need to have a time index formulation, and it gets hard. Yeah. Okay. Yep. Uh-huh.
Network formulation induce a particular basis for the error.
It does.
Can you repeat the question?
Oh, yes. So if the ALP that you get from the network induces a particular basis, right? Yeah. It is the intuition set is an indicator basis function. Instead of indicator basis, if you're in this state, you apply this. If you're in that other state, apply this based on where you are in the path. Okay, good question. Because you have this combinatorial structure, right? That it depends on where we are, you're going to go to some directions. That's why you call it indicator. Yeah, I don't know if there's a better functional structure there. Yeah, sorry. I don't know. Good question. Good question. Maybe you can find out. I don't know. Maybe it could be. Could be. I'm really interested because there's a lot of LPs. Maybe that could be another opportunity for leverage some network structure. Yeah.
So
So yeah. Sorry, my friends. Yeah. I will repeat the question. Sorry, Phoebe.
So you're sort of using the DD as a way of reformulating the problem.
Show the D to reformulate the problem. Mhm.
Can we use the DD in other ways?
So asking to if you can use the Ds besides just reformulating the problem other ways.
Even for this problem.
So you could use Jones to where maybe Jones' approach, maybe reformulate the whole. You can definitely use that. Yeah.
Did you try that?
No, I don't. Yeah, because I don't know what would be a good merging here. It's a good question. The system that they couple, I think if the system doesn't decouple.
So I mean, the point I'm saying is that you sort of use the DD in an indirect way, right? That's kind of a model.
Yeah, model reformulation, exactly.
I think that's a bit unusual. But I'm just wondering whether there's more direct ways of using this.
Well, you could, again, then it goes to the first research stream where you, if you want to use more directly, you would have to use a branch and cut, you have to relax, doing branch and bound with MDDs. You could have some approach there. Yeah. Friends.
So is the overall idea of using the DD to construct a clever extended formulation?
Perfect.
And then I'm going to like exploit the network structure of the DD
You got it.
to write the extended formulation in some way. So it's like a thinking in the DD as an inspirational way to find the right extended formulation.
Exactly. And repeating, the great question is essentially you're taking a problem, you construct an extended in an extended space of reformulation, and you're using the structure of the network, in particular it can be a DD, to find more properties that could give you more theory or structural results or computational methodologies. Yes.
Thank you.
You're welcome. Thank you for answering.
All right. I think we're out of time. So